the last video, number 6, we're going to do some hypothesis or significance testing for the difference between two means. So our null hypothesis is going to test whether the two populations really not different from each other in terms of their means. Typically, and this is the way the book says that they will always do the problems, you're always going to be looking for a zero difference between your two population means. That's what we're going to be hypothesizing, is that there's a zero difference between the two population means. But technically, there could be other differences besides zero. But the book says they will specifically only look for zero differences. So our null hypothesis could be written in one of two ways. We could say that our two population means are the same, or we could say, well, the difference of them would be zero. Okay. The alternate hypothesis will just use a greater than, less than, or not equal to. Now, back in the day, some old school, this is the way we used to do hypothesis testing for one mean. We'd have a sample mean. We would subtract our hypothesized population value and divide it by the sample standard deviation, which is S sub x in your calculators, divided by the square root of n, where we had to make sure that we put this in parentheses in our calculator. Okay? Now, it's going to look something like this. Instead of having a sample mean and a population mean, really we're going to subtract two sample means, and we're going to subtract the difference of our population means. But again, think about this. This is really from our null hypothesis, which in all cases for the book is going to be zero. So typically you can get by with just this part of the formula. You're always going to be subtracting zero in the book, but I don't know if you necessarily just want to leave this out. I would still go ahead and write it and then just say this is from the null hypothesis, or we could even shorten this down a little bit more and say this is from the hoe. And if you want to, you could even go beyond that and say typically that's going to be zero. So you're really going to be subtracting nothing. Okay, so we're going to need two sample means from our two samples. We're going to need two sample standard deviations, which we're going to square into variances, divide each of them by their respective sample sizes, add that quantity together, square root that bad boy, and make sure that's divided by the difference of our sample means. Degrees of freedom, since we will still be doing T-CDF with T distributions, and before I mentioned in a previous video that the main reason why we use T is when sigma is unknown. But what if by some crazy chance you know sigma? If sigma's known, then this turns into a Z, and this turns back into a sigma. And then instead of using T-CDF, you're going to go back and use normal CDF for Z-scores. That's going to be the only difference here. So if by some crazy chance you know what sigma is, pop it back into where it should belong and change the T back to a Z. Otherwise, we're going to stick with this formula. So degrees of freedom for T distributions. We mentioned in the last video that there were two options. There was the crazy Satterwothy formula, which was ridiculous looking, and that's the actual formula the calculator will use. Or we can just use the same thing from last video, the smaller sample size minus 1. And this will provide us with a more conservative p-value than the first one. So our p-value will be larger than it really should be. But hopefully it won't be too much larger that it would give us the wrong decision to make in the end. So there might be some times where maybe in the calculator you get a p-value that's like 0.04, and you would go, well, at the alpha equals 0.05 level, we would reject. Now, if you did option 2, which most of you are going to do, not in the calculator, it may give you a p-value of 0.055, and now you go, hey, well, I'm going to fail to reject. So if you get a p-value that's very close to your alpha level, and you use the more conservative option here, you may want to plug in your calculator, and again, I'll show you in class where the exact command is you would use for this. Do it with technically option 1, because it'll do the crazy formula for you, to see maybe what the more appropriate p-value is. Is it in fact less than our alpha value? The conditions, same as they were for confidence intervals. So I'm not even going to waste any time talking about these. So here's the example we're going to look at together. In commercials for Bounty paper towels, the manufacturer claims that they are the quicker picker-upper. But are they also the stronger picker-upper? Two AP Stat students selected a random sample of 30 Bounty paper towels and a random sample of 30 generic paper towels and measured their strength when wet. To do this, they uniformly soaked each paper towel with 4 ounces of water, held two opposite edges of the paper towel, and counted how many quarters each paper towel could hold until ripping, alternating brands. So they first started with the Bounty one. They went to a generic, went to a Bounty, went to a generic, Bounty, generic. Now, I pulled this example out of the book, out of like the, hey, here's some extra examples you could use in class. I find it odd that they're saying they used quarters on wet paper towels, and we would end up with like over 100 quarters could be held by a wet paper towel. That seems like a lot to me. Like in a roll of quarters, $10, there are what, 40 quarters. A roll of quarters is pretty heavy, I would think, for a wet paper towel. Maybe it can hold it, I don't know, but it seemed kind of a stretch to me. So I don't know. Just to let you know, maybe you're thinking the same thing too. Use a significance test, a hypothesis test, to determine whether there is convincing evidence that wet Bounty paper towels can hold more weight on average than wet generic paper towels can. So we're going to be doing a one-sided, because we are saying Bounty is going to be better than the generic. We're not saying, is there a difference between the two? And we would use a not equal to sign and make it a two-sided test. So we will again use a one-sided. And here's one way, if you wanted to write differences here, we could say, well, really, there is no mean difference between our two paper towels, so they give us a difference of 0. Or if we're calling this sub B here my Bounty, so mu sub B equals the mean strength for Bounty paper towels, mu sub G equals mean strength for the generic paper towels. If we're thinking these are going to be able to hold more weight, that this number would be larger, and if we subtract a smaller number for the generic paper towels, we would expect numbers that are still greater than 0, positive differences. Now you could, yeah, I guess I can show you that. So you can write your two parameters like this. You can leave them separately, or I had showed you in the past that you could write it like this, that really mu sub B minus G is the difference in the mean strength between Bounty and generic paper towels respectively. You can write it like this, where you're kind of making only one parameter, or, keep hitting the wrong buttons here, keep them as two separate things. Either way is fine, really. Now, we could also say mu sub B equals mu sub G for null hypothesis, and say mu sub B is greater than mu sub G. You could write it those ways. That is fine. Conditions. It specifically said there was a random sample of 30 Bounty paper towels and a random sample of 30 generic paper towels. It specifically said that we're good. Independent. Now, instead of saying, is the population of Bounty paper towels greater than or equal to 300? Is the population of generic paper towels greater than or equal to 300? We are dealing with a population that is not finite. Okay, we are dealing with populations that are extremely large. You can buy Bounty paper towels and generic paper towels at pretty much any store you go to in America. So all I'm going to say is this: since both populations of paper towels are extremely large, assume true. Okay, so I'm acknowledging the populations are very large, that they are in fact really greater than 10 times my sample size. So if you're ever dealing with a population that you know is going to be very, very large, you can get by with just saying this. That is fine. If you still want to go ahead and write out what the actual conditions are and plug in those things, that's fine. You can absolutely do that. For the normal condition, well, let's see. Was the population of each paper towel normal? It didn't say. Our sample sizes were 30 and 30. We can use the central limit theorem. So we don't have to look at box plots. Thank the Lord Jesus. So we can just say, since both sample sizes are at least 30, the central limit theorem applies to both, and we may assume T procedures. So don't worry about box plots. We don't have to worry about them. Calculations. Here's our formula. And I went ahead, really what I did here, let me jump back, was I went to my data and I said, all right, let's call all bounty stuff list 1, all generic stuff list 2, put that in my calculator. And so I knew I would need to get some sample means, some sample standard deviations. So if you go to Stat, over to Calc, and then you can do one variable statistics twice, once for list 1 and once for list 2, or you can use 2 variable statistics, and it'll give you all the bounty stuff first, and keep scrolling down, and it'll give you all the generic stuff second. So that is an option you can do there. So that's where I got all these numbers from. So now I'm just going to plug them in. So I've got these numbers over here. I've got these numbers here and here. I got these numbers here and here. The only thing I don't have is mu1 minus mu2, which I said comes from your null hypothesis, which is 0. So sweet, we've got all the numbers we need. So let's plug everything in now. Now, to get full credit again, you need to list the full formula without any numbers involved, and then plug everything in. And then I know some of you have expressed some fear, some confusion of, man, I really suck at putting this stuff into my calculator. Again, you could use the actual 2 sample mean hypothesis test feature of your calculator to really do all this for you, to tell you what the t-score is. Okay, that is an option. Oh, didn't want to do that. Now, if you put this all in your calculator, you should get 17.65, which you might be going, man, that's a pretty big number. We usually don't get t-scores that big. You don't. With a t-score that big, you should be expecting a very teeny tiny p-value. So based on that, here's my t-curve. I need to go 17.65 standard deviations above the mean. Yeah, that's really not on here, so I just kind of shaded the very end and said, hey, that's where that's at. So the probability that we get other t-scores that are as extreme or more extreme than our 17.65, aka we're going to be getting a p-value here. So t-CDF to 17.65 to infinity, degrees of freedom, I'm going to use 29 here because I take my smaller sample size, which, hey, I've got a tie here, so just pick one, minus 1, there's my 29. Plug that in my calculator, here's my p-value, which is very teeny tiny, okay? Now, if I put all this information into the calculator and have it do it for me, the calculator gave me a p-value, which upon initial glance, you're like, oh, well, that's not far away. But then, yeah, look at this. It's 8 decimal places smaller with the calculator than it is with how we did it here with the more conservative approach. Either way, you're rejecting most definitely. But the calculator said the degrees of freedom, and this was even a rounded number, 57.84 degrees of freedom, which is very odd because you don't normally have decimals with degrees of freedom, but you do with that Satterwothy formula. So anyway, conclusion. We do absolutely have enough evidence at the alphas 0.05, even at the 0.01 level, to conclude that bounty paper towels do hold more weight than the generic paper towel. So in the paper towel arm wrestling match here, bounty, boom, over the top, Sylvester Stallone style. He gets his kid back, and that is a happy story and a happy ending. Here is the problem I would like you to take a look at and bring to class. I know only 3 of you are going to do this. Thank you for doing this. Those 3 people, you will probably score very well on your next test. Whew. Now, you will notice that each of our 2 samples here, only 5 each. So whenever you check the normal condition, yep, you're not going to be able to use central limit theorem. You're going to have to make some box plots, but that's fine. Put it list 1, list 2. Remember I showed you in the previous video how to do 2 box plots on the same screen at the same time. You just have to turn on both plot 1 and plot 2 and make sure that you tell it to graph the appropriate list. Make sure one's for list 1 and the other's for list 2. So finish this up. We'll do it tomorrow in class. Adios, and we are done for the chapter.